Alright, everybody. This is on the computing power of Minecraft Redstone. Okay? First, let's just have a quick refresher on digital logic, binary representation of data, and logical operations. So the first thing we're going to talk about is what exactly is binary. Right? So when we're talking about binary, we're talking about a numbering system where you only have 1 and 0. Your two possible ways to represent something. And so it doesn't have to be numbers, it can be anything that you want to represent. Like, if a coin is coming up heads or tails, heads can be a 1, tails can be a 0. And if you want to represent more different states or variables, then you can, let's say, the dice. You have 6 possible dice, and so if you have 3 bits, 3 different numbers, we can have some sort of encoding where if we want to, actually something more relevant to this presentation is talking about tic-tac-toe, right? So if we have a C cell in tic-tac-toe, it can either be X or O. So, or it can also be blank, right? So if we're going with just 1 bit of data, then we don't have enough information. We can't store blank X or O. We need the second bit to store whether or not it's an X or an O, or if it's blank, right? So if it's blank, then we can say that's 0, 0. If it's an O, we can call that 1, 0. And then if it's an X, we can call that 1, 1. Right? So that's just an example of how you can encode things with binary. Okay. Next, I'm just going to go over all the different logical operations we can do. Welcome. So the most simple one is the NOT gate. So if you have an input of 0, it gives you a 1. If you have an input of 1, it gives you a 0. Simple as that. It just inverts whatever input you give it. Next is the OR gate. So if either A or B is turned on, then the output C will be turned on. Right? Then you have the AND gate, which is if A and B are turned on, then it will output a 1. Otherwise, it'll output a 0, no matter what. And then finally, the XOR gate, which is an exclusive OR. So the only difference between this and the OR gate is that if both are on, then it turns off. Right? Only one or the other can be on for the XOR gate. And this is a very important one, so keep that one in mind. Alright, now, first thing we're going to do before we get into Minecraft really is just a refresher on how Redstone works. So, Redstone is a simple circuit simulator, kind of, in Minecraft, where you take a lot of the complex parts of circuits in real life and kind of simplify it so that, kids can play in the game. And so, you can do pretty cool things, of course, but you can also do anything. All computation, anything is possible. And you'll see that pretty soon. So we're going to go over something simple here, just inputs. How can we carry signals? So we've got the button, the lever, and the pressure plate. Those are the 3 most basic ones. So when you have the button, when you press the button down, it'll power that block, and whatever is adjacent to that block will be powered. So that lamp on the bottom will be powered when you press the button. But then it will depower itself. Then the lever is a switch, so you can turn it on and off, and it will keep that state. And then the pressure plate will turn on whenever you are on it. Okay. Next is wiring. So when you are trying to carry a signal from one place in Minecraft to another, you use the redstone dust, which is the red stuff on those stone slabs over there. And what it does is, when you have a lever inputting into that wire, it'll carry that signal up for 15 blocks only. Okay? And that's because it was convenient for the Minecraft developers. With binary, you can store as many as 2 to the power of how many digits you have. So a 1 bit of binary, you can store just 2. 2 to the 1 is 2. And then 2 bits will go to 4. And with 4, you can get to 16. So 0 to 15 with just 4 bits. And so it's very easy for Minecraft developers to just put that in a 4-bit number. And so wiring has to be planned very carefully because wiring will interfere with each other if they're right next to each other. It needs to be a block of space if you want to have 2 separate signals. And there's 2 different ways to move are three different really ways to move the signal vertically. So first you have the staircase, where you have redstone wire coming out through the staircase, and it goes both ways, as you can see in the video. Right? But with the slab tower, it takes up a lot less space. You can do it in kind of 2 blocks, but it only goes upwards. You cannot make it go downwards. Right. Okay, so next we're talking about power. So in Minecraft, you can have strong and weak power. So with weak power, you have a redstone dust rather than a repeater going into a block. And when that happens, whatever is directly on that block will get power. But you cannot transfer that power from that block at all. So in this case, all of these blocks here are weakly powered by this redstone block, which is the block that just gives power to whatever is touching. And in this case, this block is strongly powered by this repeater. And so the dust beneath it is getting powered because the dust counts as a block even though it's transparent. And so it will be powered by this block and power the redstone lamp and turn it on. Okay? So, just like I was talking about with strong power, the next component we're talking about is the repeater. So the repeater is probably the most important component in all of redstone because it has 4 different functions. And one of the most important is how it can strongly power a block. So you can see that, so at this moment, the PowerPoint doesn't make this very easy.
Ooh, how embarrassing.
Yeah, bro, why are you talking shit? Keep your damn mouth shut.
Just keep recording.
Keep recording, bro.
Bro, that's the only reason you're here. The only reason you're here. I'm kidding.
Before I have the repeater there, this block is only weakly powered. The redstone signal doesn't carry across into the lamp until we add the repeater, and it will strongly power the block and power the lamp. Okay. The next thing the repeater does is that it's directional. So, relevant to what we're doing in class is the diode. So if you have signal coming in from the left of the repeater, it will carry over to the lamp on the right. Otherwise, it won't pass through. And you can see that in the video like this, right? So in the first one, right here, when I turn on the lever on the left, it powers both of them. But on the right, it only powers one on the right because it doesn't let the signal come through. Okay? Next function is repeating, right? So I mentioned earlier that a redstone signal will only carry on for 15 blocks before it dies. And I have this texture pack that will show you exactly the signal strength on each piece of wire. So if I turn this on, you can see that it travels along the wire until it reaches here, where it only has a signal strength of 1, right? And so it cannot reach the lamp on the other end until we add a repeater, okay? And now the repeater will take whatever is here and increase it all the way up to 15. And so I could take that on for another 15 blocks if I wanted. Okay. And the last thing that the repeater can do is it's a delay. So the more, yes, Aiden?
Why the fuck is it 15?
Why is it 15?
Like I've been playing for a long time and I was like, why 15?
Yeah, because you only need 4 bits to store that.
Oh,
Right?
yeah.
So you can store it in just one hexadecimal number.
because if you have the 16, it's fine.
Yeah.
Yeah.
Right?
I didn't think of it like that. I thought Mojang was just like, fuck it, 15.
Yeah, they just chose a random number. No, that's not what it is. So the delay, that's every time you right-click a repeater, it will increase the delay by 1 tick, which is how Minecraft handles time in the game. 1 tick is about a 20th of a second, and so a 1 tick delay will be 1/20th of a second of a delay. When you press that button, it'll take 1 tick for the signal to get through the repeater to the lamp. And then as you right-click it more and more, it goes to 2, 3, and 4 ticks. So you can see that here. By default, it's just 1 tick. I right-click the repeater, now it's 2 ticks. Right-click it again, 3 ticks. And you see it takes a little bit longer for it to both turn on and turn off with the button press each time. Okay? Next component is the piston. So there's 2 types of pistons. There's, on here, there's the sticky piston, and up here there's the regular piston. And the regular piston will push, but it cannot pull. But with the sticky piston, there is slime on the face of the piston, and so we'll pull as well as push. Well, what's interesting about the sticky piston actually is that with all pistons, they take 1.5 game ticks to extend and 1 tick to retract. But all block updates happen across 1 tick no matter what. And so what you can do is if you give a piston a pulse of just 1 tick, then it will start to extend, and then after 1 tick, the piston is not done extending yet. But since block updates happen in one tick, then the block will move across here while the piston is not fully extended. And so when the pulse ends, when you unpower the piston, it will retract. But according to the piston, it's not touching the block anymore. So when it retracts, it won't pull the block along with it. And so you can have it just spit out the block with a 1 tick pulse, like this. And I had to train really hard for this, but I right-clicked the piston with a 1 tick pulse right here. You can see that. Like that. Oh. Thank you.
You didn't use another clicker?
Okay, so next, so we've got past that.
Another clicker.
There's one more component I have to show you. Actually, there's the comparator. This is going to be important.
Oh gosh.
This
is
There's gonna be a quiz. Oh no.
How many slides is dedicated to just the comparator?
This is 40 slides long.
So that'll be in a separate.
I don't know.
The comparator is it's not showing the Minecraft. Okay.
Comparator goes hard.
We're going to the Minecraft.
Comparator.
We're going to the Minecraft. This is what I'm showing the Minecraft.
You stressed me out.
Put it on Minecraft. I already told him no.
You stressed out.
I mean, he said it.
He did?
I know, but then it was flashing. I'm being a good student. You are. I can tell you can't rank glasses.
Yeah, so all it does, I can see Minecraft.
Yeah.
Projected over 60? I guess so, Dude. So the comparator I call compare mode. So if the input signal strength is greater than the output than the side signal strength in here, then it'll output nothing. Right? So if I give it a signal strength of 15 on the side and a signal strength of 14 on the input, then it'll output a 0 because the input is less than the output. I mean the side input. But if I give it much less than that, a 10 for example, then it will output 14 over there. But if I set it to subtract mode, then it will go to 4 because 14 minus 10 is 4.
That's true.
Wait, sorry. Is that that we learned about in logic the first time? That like thing
So,
with
when we have 14
Subtract mode goes
on the
hard.
input, and 10 on the side,
the PN thing.
yeah, 14 minus 10
It's 4.
is 4.
That's
Okay, 4.
Dang, Axel, you're good.
And the signal dies to these
Axel.
We didn't know this.
So is the other mode just like?
I didn't know that.
No, the other mode is compare mode. So if it's just a simple if the side input is less than the the back input, then it'll output. Otherwise, it won't.
Okay. Oh, so that's the back input then.
And then the other mode.
Yeah, like that.
Holy shit, we're gonna do the other mode again?
Yeah.
I'm really gonna see that.
Right.
Also, so say for theory, you put like a pull strength of like 12 into the back of it, it would output a 12 strength.
Yeah, that's right.
Okay.
Oh, it outputs.
Yeah,
It
does the 12 again.
Yeah,
Yeah.
because it goes in 14 and outputs a 14.
Yeah, that's right.
Oh,
Yeah, that's a pretty useful part of the comparator as well.
It just extends the signal
Yeah.
one. That's cool.
Yeah, that's
so
right.
that was
Oh, yo!
Dude, I'm just like,
I'm
like mind blown.
It's okay.
For the extension, it's when you kind of control how
TikTok?
Oh, shit.
All right.
On Windows app. That's the first time I've actually understood comparators.
Yeah, really.
I didn't really like. It's almost like all we learned is
Okay. So next thing we're going to go over is just logic, because we've went over Redstone now, we've gone over the basics of logic, and now we're going to go over how we do it in Minecraft, right? So in Minecraft on its own, we only have OR and NOT as the two gates we have built into Minecraft. But what's interesting about that is that from just OR and NOT, all logic can be created with that. And if you have all logic, you have all computation. Any calculation, any operation can be done entirely in Minecraft. Right? And so the way we do NOT in Minecraft is just with a redstone torch, right? So the redstone torch by default is powered, it's on, and so it's powering this redstone lamp. But when I turn on this lever, the dust up here will be powered, which will power this block and turn off the torch, right? So if you look at that, that's just a NOT gate, right? If this lever is the input then right now the lever is set to 1, and so the output is 0, and vice versa. And then this is OR, right? And in Minecraft, OR is as simple as just connecting two different redstone inputs together. If you look up there, there's redstone dust on top of the blue blocks connecting the two levers together, which will just go out to the lamp, right? So one of the levers is on, or both of them is on, it'll turn on, okay? Okay. So let's try to do something more complicated. Let's try to make an AND gate, right? So I said that we can do everything with just OR and NOT, right? So let's do it.
Bro walks in, special guest.
Okay. So
Especially when I'm actively blinking about it.
okay, so first things first. All right. First things first. Let's take a look at this truth table. Okay. So 1 and 1 is the only way we can produce a 1, right? That's going to be. It's kind of weird to think about that in Minecraft. So let's consider the opposite. Let's consider everything except for this is a 1, right? What that means is if either of these two inputs is off, then we want a 1, right? Well, I just showed you that it's very easy to make something where if either input is on, then we get a 1, right? So 1, 1, and we get a 1, right? But how do we get it so that both one of the inputs is off, then we want it to be on? Use the NOT gate. That's right. That's right. That's exactly right. Okay. So if I do that and do that, then we have both inputs inverted going into an OR gate, right? So if either of these inputs is off, then the output turns on, right? So if this one is on, if this one is off, then the output's on. If this one is off, the output's on. But if both of the inputs are on, then you can see that it turns off, right? And so this is the inverse of AND. This is a NAND gate we've created right here. So somebody tell me how to make this into a AND gate?
Put another fucking torch.
Put another fucking torch on it.
Yeah!
All right. So now we have an AND gate, right? So unless both of these torches are turned off, both of these levers are turned on, we're not going to get anything on the lamp. When we turn them both on, we get something on the lamp. And so there's AND right there. Okay? So the next gate is the exclusive OR. And this is really important for addition, which you can do in Minecraft. I was going to add addition to this presentation, but it was getting just so long, I decided to skip over it.
So you told me you might have to have a part 2.
Yeah, maybe I will.
So you told me you had to subtract addition?
I did have to subtract addition. Yeah, it's crazy. It's crazy.
Yeah, 41 slides too much, you know.
Really was.
Okay, so what? Let's look at the truth table here, right? So it's the same thing as we only have 2 ways to get this to turn on, right? If A is off and B is on, or if A is on and B is off. And so what we can do here is create 2 AND gates and then OR them together. So something like this, where we have an AND gate, another AND gate, into an OR gate, right? And so if we have A and B, right? Like that. Welcome. Right? So if we create this circuit here, we'll have the inverse of A and the normal B coming together, or the inverse of B and normal A coming together. And if either of those 2 inputs are on, then we get an output of 1. Right? And so we can create that in Minecraft like this, which it looks very complicated, it's huge, and but basically the way this works is when this input comes in, it'll turn off this torch. If this input comes in, though, it'll turn on this repeater and turn on this redstone line. And so both of these redstone lines are connected to inverters, which are then ORed together and put into the lamp, right? So if I turn on this one, then you can see that this torch turns off and depowers this line, which allows this torch to turn on and turn on the lamp. Otherwise, we can do this, and it's the opposite. Interrupt me! Jesus!
Yeah!
Get out of here!
That's it.
My
We bang it.
Go! Get away! Get away!
Oh my god.
Jesus Christ! Okay. Anyways, this is just the opposite. This is the other guy in reverse. And so if I turn both of them on, both of these lines will get powered by these repeaters. And so none of the torches get to turn on the lamp, right? But like I said, it's huge and complicated, and I don't like it. It's ugly. So we can use comparators for this. So can somebody, let's look at this configuration right here, actually. Can somebody tell me what's going to happen? This comparator is in subtract mode. And so if I turn on this lever, it's going to be, yeah, it's going to be 0. It's going to be 15 minus 15, which gives you 0. Nice. Very nice. Okay. Okay, but what if I put another one next to it? Right? So if I turn on only the left guy, what happens?
Then that one turns on as well for the bottom, and then the top one, or the other side isn't there. So
Yeah.
that means it would go through on the right side.
That's right, yeah. You would get 14 on the top right and 0 on the left, like that. Right? Yeah. And then the same thing over here, right? You got 14 here and nothing outputted on the right one, right? But then if you put them both on, then they both disable themselves.
Yo, he's cooking! Oh my god.
God bless the comparator.
God bless the comparator.
What, a PN junction or something like that?
What's that?
Is it a PN junction or what is that thing called?
Oh, not you knowing too much.
The comparator is...
Yeah, it's,
Yeah, you can't really... It's weird. There's no real life equivalent of the comparator, really. Like,
I mean,
it does so many things.
It's like that thing.
It's
but
just a
except
broken down
Yeah.
current doesn't carry through with the added, you know.
Aaron's like my dad on Christmas right now.
He asked me to record.
No, when you're getting kids. Wait, he has to turn the camera to himself.
Yeah. Can you show them? Okay. So. All right.
Oh, it's not. Oh.
So, next section. Storing data in Minecraft. How are we going to do that? Huh?
Big jump ball, buddy.
Alright. So, SR latches, flip flops.
Yo,
You guys ready?
Well,
So here's the SR latch, right?
20-minute.
Okay. Well, you can make it in Minecraft. And it's actually really easy to explain it in Minecraft versus with this logic circuit and truth tables, right? So, I was originally going to do it in the presentation, but I think it's better if I just show you in Minecraft, honestly.
Yeah.
So,
That 120 FPS.
yeah, exactly.
Man got a whole fucking quantum computer over there.
You haven't seen anything yet. Okay, so right here we have an SR latch, okay? So let's look at what's going on here, okay? So right now, this torch is on and powering this line of redstone, which is going into this block and turning off this torch. So right now, this torch up here is locked in the off state by this one, okay? Until I turn on that button and depower this torch, which will allow this torch to turn on and lock this guy in the off state. And so we switch what's going on, right? So we have like that, right? And then it just happens in the opposite direction now. So we can do this one and put it into the opposite state, right? So now we have an SR latch, right? You got set and you got reset.
Bro, I'm about to ask. You already know what I'm about to ask.
What are you gonna
I'm about to ask what the target block does again, because I ask every time and I forget.
Yeah, sure. Okay.
So it
So
does something special.
yeah. So
Show a specific problem.
okay.
It's superconductor.
Yeah, that works. Okay, so let me think here. Yeah, so if I do this, right?
Yeah, that's not gonna work.
It's not going to turn on the lamp, right? Because it's not, the redstone line isn't going
Yeah,
into
it's
that.
not, yeah.
But when I put the target block down, it'll kind of steal power from the line.
Okay, gotcha.
So it's kind of like running a repeater into a block without having to use
Exactly.
extra space.
Exactly. Yeah.
How the fuck you make this block?
It's
So,
just
when
Yes.
Mojang was coding the target block in, obviously like it's supposed to be you shoot arrows at it.
Yeah, yeah.
Do you think that that mechanic was intentionally added to like fill a gap that some developer saw in like the scheme, or was it an accidental thing,
No,
result of?
I mean, the way you use the target block is not like that. You use it with comparator.
some signal.
Yeah.
when it's hit.
Oh, you don't even use it with the redstone directly out.
No, you use comparator. So it would have to be intentional.
Because since it has to emit a signal.
So in theory,
Thank you for answering my question.
we can shoot a boat and then they will turn on.
Yes. Yeah, that's what the target block is for.
Can you show us?
Can you show us?
Sure. You got aim? I don't know, guys.
No.
This is the part where you put a comparator next to a lectern and you get an alpha signal based on
I think you can make it so that the input that the tick button that you're using on the SR latch is just another target block, and you have to shoot it to target
I like that.
it. And then it stores the bit as well. That's a good way to do tracking for like a.
All right, there you go.
Parts have never been modeled.
Oh shit, it gives you
Yeah, exactly.
And also, the worse I am at aiming, the less of a signal strength it's going to give me.
Oh yeah,
Right.
it gives it.
He gives me a 4 that
You get a
time.
My
score.
God.
Right? Okay.
Score translates into
That is
energy.
very.
How is accuracy has the power. That's crazy.
That's right, man. That's right.
Accuracy is power.
Gaming is power. Being a good gamer, that gives you
Make an
power.
equation based off
Making a redstone circuit, but do you have vectors and comparators?
All right.
I'm on page 14.
all right.
I'm on 14 signal strength.
So the next thing we got in
That's the thing.
on the docket is the T flip-flop, right? So the T flip-flop is useful. What it does is instead of having a different button input for setting and resetting your output, you can instead just have one input that will flip whatever state you're in, right? And so the way this works is if the output is on, then the signal will go through this AND gate into the reset. If the signal is off, and the way the SR latch works, if you can see, one of the inputs will always be the opposite of the other, right? So we can say Q and Q9, which is the inverse of the Q output, right? So, but essentially, you can think of this as just taking the output and inverting it and setting it over here. So if the output is off, and we get T, then we want to send that into the S signal, right? So if the output is off and we get an input, then we want to send a signal to the set, right, to turn it on. If the output is on and we get an input, we want to send the signal to reset to turn it off, right? Basically flip whatever state you're in. Okay. And so we can make that in Minecraft this way, and it's very complicated. It's big and ugly, but basically what you got is an AND gate here. So you have the inverse of, or you have the output here, and then an inverse of your input here, and then the inverse of that going into the reset, right? So if it is off, if the output is off, and you give it an input, then it'll go into the reset. And then you have the inverse over here going into this guy, right? So if I give this a quick pulse, then it'll go on. If I give this another quick pulse, it'll turn off, right? So we got a T flip-flop right here. But the thing is, Minecraft makes this a lot easier for us. We don't need all this logic to do a T flip-flop if we have the 1 tick pulse from earlier, right?
I know where we're going.
Yeah. So when we push this button, the repeater will power this piston, which will push the block up. And if you remember, the block will update itself within 1 tick. So a 1 tick pulse will be sent through here into this piston. And a 1 tick pulse going into a piston will cause it to spit out the redstone block. And if redstone blocks give power, then we can take a signal from this block right here and say that that's our output, our Q output, right? So if I press this button, the piston spits out the redstone block and turns on the lamp, right? And then if I press it again, it'll reset that. So it'll just do the opposite of its current state, which is exactly what a T flip-flop does.
I didn't say actually show us this, bro.
I know, you really.
You better donate this to the college. Let the students see this.
Yeah.
We will be spitting out the best computer engineers.
Oh, for sure, for sure.
48 minutes.
Yeah. Okay, the last thing in memory for Minecraft is the is repeater locking. Okay. So repeater locking is when you have a repeater that is powered, going into the side of another repeater, and you get this sort of bedrock texture on the repeater, right? And so what happens here is you just, no matter what, this repeater is locked in the on state. So if I depower it, it still stays locked in the on state, right? But if I depower this torch really quick and allow the repeater to read the signal that it's getting from the back, and then re-lock it, then we can basically write to it as a simple memory cell, right? So no matter what I do here, the repeater stays off until I hit the right button, right? And then it turns on, okay? And so what I've made here is a
do that again?
right? So whatever is on the input, the lever, will be written to the memory cell whenever you have a right input, right?
I would have passed logic.
Yeah, and so this maybe I should have done this last year. So that's it for memory, okay? Now, the final part of this presentation, we're talking about tic-tac-toe, okay?
Me drawing fucking my sensor.
Yeah. So,
You got 13 slides for tic-tac-toe?
something like that.
Yeah.
So,
I'll beat you.
so let's, so first thing we need to talk about is that, like, everything I've given you so far is all we need to make tic-tac-toe. Like, everything in this presentation so far is used in my tic-tac-toe system. So let's just talk about exactly what needs to happen for us to make tic-tac-toe, right? So what we need to do is, if we have tic-tac-toe, we just have a simple grid, 3 by 3, right? And it can be either X or O. And if we have 3 in a row, then we have a win, right? So what do we need? Let's create a list of what exactly we need, right? So what's the first thing? The first thing I mentioned. We can either have an X, O, or blank, right? Yeah, so 3 states. We need to store 3 states, right? And the next thing we need, wind detection, yeah. And also, a lot of tic-tac-toe games end in a tie, so we need tie detection. Uh-huh. And then also, we need a way to keep track of, whose turn it is, yeah. So turn, right? Okay. So each one of these we can do with a different component, right? So, or a different set of components. So let's talk about the first one, storing 3 different states, right? What do we use for that? We can use... Yeah. 2, how many latches?
That's a damn great question.
It is. What do you guys...
2.
What
2.
Since it's
That's right.
Is it 3 finding states?
That's right.
States?
That's right.
Okay.
It's a miracle.
That's the shoe effect.
Alright, so let's talk about exactly what we mean by storing 3 different states, right? So we need to come up with an encoding, is what it's called, right? With how exactly, what exactly each thing means, right? 0, 0, 0, 1, 1, 0, and so on, right? So it'd be easy to kind of just say that, okay, blank is 0, 0, X is 0, 1, and O is 1, 0, or something like that, right? But when you look at like those values, right? If we want to do something like wind detection, checking for equality, right? Because that's how we would do wind detection, right? Is we would check if 3 different cells have the same value stored in them, right? Trying to do that for these is kind of complicated, where we need like maybe an XOR gate on each bit or something like that. But if we do something a little weird here, we could actually say that this first bit is whether or not it's occupied, right? And this bit is whether or not it's an X or an O, right? So instead we can say that a blank cell is 0, 0, an O is 1, 0, and an X would be 1, 1, okay? Yeah, okay? And so now, yeah, and so now wind detection becomes, well, time detection becomes incredibly simple, right? I mean, all we have to do is, if a cell is occupied, then this is 1, otherwise it's 0, it's empty. So we just need a 9-input AND gate, and we're good.
After,
Yeah.
all of them become ones and the wind detection hasn't triggered yet.
Exactly, that's right. Yeah, and for wind detection, it's just a little bit more complicated, right? We can create something like this, right? So if we have the occupied, right, and let's just call it value, I guess. Okay. I actually have this already drawn out, so let me switch to that. Okay.
Oh yeah, you've done this next week class.
All right. So what we can do here is, so the wind detection, we need to make sure first of all that they have the same value, right? So if we have A, B, and C are our 3 cells, right? We want to make sure A, B, and C have the same value, but we don't want it to work if everything is blank. That's not what we want. So we need to first make sure that all 3 of the occupied signals are set high, right? So to send them into a 3-input AND gate and out to this AND gate, right? So this wind detection can only turn on if all 3 of them are occupied. And then here we just have, this one says if all 3 of them are in X, we want to go and output a 1. And this one says if all 3 of them are 0, because this is an OR gate but inverted, right? So if any of them turns on, then it'll turn off, right? And then we send that into the OR gate and into the AND gate, and we get a win, right?
I just understood why encoding is important.
Yeah.
Because this would have been so hard to think of if you didn't encode it.
Exactly. Yeah.
Oh wow, that's
Uh-huh.
crazy. I
Uh-huh.
think I just passed signals and electronics and everything.
Oh, well, let's just not go that far. We ain't there yet.
Okay.
Computer org.
And then,
This is about, this is signal. Top organs act.
No, it's just see the force number, bro. It made a lot
all right.
of
Next,
sense.
let's talk about how we're going to display things, right? So there's a simple way we can do it is we only need a 3x3 grid of pixels really to display these things. You can have the X look like that, and the O look like that. And so how exactly do we go from our encoding we came up with, where we have 1, 1 for X and 1, 0 for O, into these kinds of signals? Well, we can use something called decoding, right? Where we take a binary number and decode it into whatever signal we need, right? And so we can take advantage of certain things here. First of all, take a look at these two and notice that in either case, the corners are turned on, right? So we can simply tie these 4 corners to the occupied bit, right? If it's occupied, turn on the 4 corners, right? And then for differentiating between X and O, if the XO bit is set to 1, then all we have to do is turn on the center and turn off these guys. And if the XO bit is set to 0, then we turn off the center and turn on these 4 guys, which I call the cross, right? And so we can create a pretty simple logic circuit for that as well, where we can have the corners simply tied to the occupied signal, the cross tied to the inverse of the XO signal and the occupied signal. So we don't want to display anything if it's not occupied, right? And then the X is turns on the center. We need to make sure that both A1 and A0 are on, because that's how we encoded the X and send that up to the center. And so let's go ahead and try to make that in Minecraft now. Yeah? So, okay. So if we're using a display like this, where we have 2x2 redstone pixels arranged in a 3x3 grid, because that's really the easiest way to do pixel displays in Minecraft. You can't really individually control one lamp, because lamps are weird. Yeah, they kind of are, man. They kind of are.
Yeah, I think I already asked you about the quasi connectivity.
Yeah, I didn't want to go over that because it's just such a.
Yeah, fuck that.
Yeah.
Wait, then how the fuck did you? Why did you do like power off the lamps adjacent to it?
No, it's because you can very easily power multiple lamps at the same time, right? So if we have 4 of them in a 2x2 grid, then that's very easy to just power all 4 of them.
Yeah.
Right? Okay. Is to just handle powering and depowering the 4 2x2 pixels, right? So let's go over here, okay? So if we have our 2 inputs here, let's say that this top one is the occupied signal, right? Right now it's blank, right now it's occupied. And this one is X or O. So right now, this is an O, because that's what we decided. And right now this is an X, because that's, 1, 1 is X. right? So how do we, so let's talk about the corners first, right? So let's take a look at our schematic. So A1 just goes into the corners. So if this is A1, and we say that this is our corners bit, then let's actually put that over here.
No matter what the corner's gonna be on, whether it's.
Yeah, that's right. Okay. And then we need the center, right? So let's say this is the center. Well then, what does that need? That needs an AND gate for A1 and A0, right? So let's do that.
A0's gotta be a knock.
Yep. So A1 not, A0 not, or them together like that. Put a torch down here, and there you go, right? So two inverted inputs going into an inverted OR output, and so 1, 1 will give us the corners and the center. Okay. Now we have to handle this guy being on and this guy being off. Okay. So, okay, first thing we can do is get the A1 signal. So if A1 needs to be on, then from how we build AND gates in Minecraft, we need to take the inverted version of that signal. So we can take the inverted version of that signal and bring it down here, and then we can take just this signal here, and let's take it like this. So we can like that, all right? Okay, and then we invert that. And so if we give it a 1, 0, then it should turn on the cross signal and the corner signal. Okay? And then if we turn this one on, then it'll turn off the corner, the cross, and turn on the center. Right? And so that's what I've built over here, is just all of that logic put together. So you have the 4 corners here, all connected up to just A1, right? And then you have the center here with that same AND gate design, where you have this guy coming into this block, coming into this, and then this guy has the inverted output going into that, and then onto this redstone, thus inverted going into this to the center, right? And then the opposite of A0 ANDed together with A1 going into this block, this line, which through these target blocks goes up to the rest of the cross, okay? And so we can just show that off right now. So 1, 0 should show me an O on the lamps, which it does, okay? Because this AND gate down here is turned on, right? And which goes into the cross, which turns on all 4 of the cross signals. And then if I turn on this guy, the AND gate of A0 and A1 will turn on, turning on this torch, which will turn on the center and give us an X, right? Okay, so next thing we need to do is talk about memory, right? How are we going to store X's and O's in our Minecraft creation? Well, first thing we need to talk about is, obviously we need 2 SR latches, right? We also need to make sure that we have a way to store the turn, right? So whose turn it is always switching, right? It's X's turn, then it's O's turn, then it's X's turn. So what kind of memory would be perfect for that? There's
JK flip-flop?
no.
Wait, he said the JK.
Not the JK flip-flop.
SR?
Huh?
SR?
Yeah, but there's a specific, something I mentioned earlier in this. The T flip-flop.
Oh, yeah, it's called
Dude, he was like the professor. He got the professor years.
You just don't listen to one black guy.
Yeah.
It's my history.
I'm sorry. Okay. My ears
He was doing the whole.
I'll only answer you now, Brian.
Bro.
Okay. Okay, so yeah, the turn flip-flop, we can just say that the turn is handled by a flip-flop called a turn flip-flop. And so, and what else? We need to make sure that it can't be overwritten, right? So if the top signal A1 is on, then we can't let the bottom be overwritten no matter what, right? So we need to have something like this, right? So if A1, so this is the inverse of our outputted A1 signal, right? So if A0 is off, then that'll go into this AND gate. And if it is X's turn, then that'll go into the AND gate, and the right signal will go into the AND gate. And so all of those will set the bottom SR latch to 1, which will set a 1-1, right? So let's actually back up with it, because each memory cell needs to have, if we're going to have the user input which cell they want to write to on, let's say, a panel of buttons, then we need to have one line of redstone going into each memory cell from the button panel. So we can call that the write input of each memory cell. If the user presses that button, we need to write something to that memory cell, whatever it may be. And we can determine what we need to write to it based on that turn signal, right, from the flip-flop. Okay? And so no matter what, if the write signal is turned on, then we just need to write a 1 to the occupied bit, right, no matter what. But the bottom guy who's handling X or O should only write a 1 if it's X's turn, right? Otherwise, it should just write a 0, or stay as 0, because it's 0 by default. And then when this guy is turned on, it doesn't let the bottom guy be written to anymore until we hit the reset. Okay. So let's build that. So what I've got here is just two SR latches on top of each other with their resets linked together here through the slab tower, right? So if I were to set both of these guys like that, right? We get an output of 1-1 on these lamps, and then I hit the reset, and then we reset both of them. Okay. So let's take a look at how we can make it so that it can't get overwritten, right? So all we have to do, the top one can't be overwritten no matter what, because it's always going to get set to 1, and you can't reset it to 0 without hitting that reset input. But the bottom one, that one's the tough one, because it needs to be able to stay a 0 no matter what. So what we can do is take the inverse of this signal. So if this is on, we need this to be on, so we take the, we need it to be off, right? So we need to take the raw signal, because in Minecraft, that's how we make AND gates, okay? And so, let's take that. Okay. And then, let's take another inverted signal, right? So, if this is our right button, okay, when we turn off this torch, it'll turn off this redstone line. And so we can say that this is our right output. This will write to the cells, right? So if we turn this on, you'll see that the right torch will pulse very briefly, okay? But if we were to set this guy to occupied, then it won't, right? It's being powered by this torch over here. And so it won't turn off, and it won't allow anything to be written to the cell, okay? Until we reset it, okay? So now let's connect this up to the right input of this guy, okay? So we can just do something like this, right? Put a redstone dust there, and so I can write to it. And now this guy can't be overwritten, it won't do anything, okay? Then we need to take this guy, okay. Okay, I can just show you. I already built it over here. So, the way it works, you have the inverse of this guy coming in and creating an AND gate with the turn signal coming in through here, and the write input through here, right? So that comes through here, and you have the output of the occupied cell going up through here, and it's also being given the right button press. And so what this is doing, this yellow part, this red part over here, is this is an edge detector. So the way we can switch whose turn it is whenever one of these cells changes their state, then you can change whose turn it is, right? So if something gets written, then that means somebody's pressed a valid button. And so O has just placed down itself because the state has changed. And so we need to send a pulse to the T flip-flop who handles whose turn it is, okay? And so in Minecraft, it's very easy to make an edge detector. In real life, it's a little weird, which is why I like Minecraft better. Yeah, so, yeah, it really is. Okay, so yeah, so if you take a look at this, what's going to happen when I destroy the torch is that the repeater will be able to, it will be instantly depowered because the repeater will lose power, but the dust won't lose power until the repeater's done being delayed for one tick. And so it will send out a one tick pulse as it reads the pulse behind it, the dust behind it. Right? And so you can see that, like that, right? You see that? There's a quick pulse on the falling edge of the signal, okay? And so if the write signal is going to turn off whenever a valid write input is given, then we can take the falling edge of the write signal and feed it into our T flip-flop here who handles whose turn it is, okay? So if we send a write input here, a write signal, then, and right now it's O's turn, right? Because the turn flip-flop is outputting a 0. So we'll write a 1, 0 to this memory cell, right? And that's what you see here, 1, 0. And then we also saw that the edge detector triggered and triggered the T flip-flop to change whose turn it is to X's turn. And so if I go ahead and reset this now, and then hit the right button again, we get a 1, 1, okay? Okay, so now we got the memory cell done. Next part is wind detection. So all we need, first of all, is to make sure all 3 of the occupied inputs are turned on. So we just create a 3-input AND gate like this. Like that. Okay. And then for this guy, we can create another 3-input AND gate like that. And then just take the inverse of that and give it to our friend here. Okay, so what's going to happen here is we've created basically a 6-input AND gate. So we have the inverted, these guys coming in, inverted these guys coming into an OR gate, and those two going into an AND gate. And so if all 6 of them are turned on, the lamp should I didn't turn these on. There you go. Yeah, lamp turns on. Okay. And then all we have to do for that last part is, if we go back to the wind detector, we need an AND gate here for detecting if they're occupied, an AND gate here for detecting they're all X's, and then we finally need that NOR gate down there. So an OR gate is just connecting lines together. A NOR gate is you just invert that, right? So we can take that and also feed it in, okay? And so if I have these 3 turned off, then that'll also turn on the torch, right? And so we've created a wind detector. So if we have 3 different memory cells being fed into this guy, it can detect if, let's say, all on a row are the same value, or a column, or all in the same row, or both of the diagonals, right? So in the real circuit, we'll have to build 8 of these red circuits to detect 3 columns, 3 rows, and 2 diagonals, right? Okay. So now I'm going to move on to, so that basically we've got everything we need, right? Tie detection, that's just a 9-input AND gate, and that is just as simple as building a 2-input AND gate, which I've already shown you how to do. So I'm going to move on to how everything is put together, right?
Man, you gotta see the speed running.
Yeah. So this is my tic-tac-toe machine. I've just
I did some off camera.
I did some good off-camera work.
Some money off.
So yeah. So you recognize this circuit from the other world?
Real life breadboard.
Yeah. I've just copy and pasted the display 9 times.
Bro, how did you roll that? Roll that?
It's just what he taught us times 9.
Yeah, I mean it is.
Yeah, exactly.
It just looks big as fuck.
Yes, because it kind of is. And then you have the same memory circuit. The same. Same memory circuit over here, copy and pasted 9 times again. And then you have the T flip-flop here for the turn detection, or turn storage.
That's a big boy.
Yeah, the reason it has so many slime blocks, is so that we can extend the T flip-flop all the way down. It's because, as you saw, slab towers only work going upwards.
Wait, question.
Yes.
How do you know like where you messed up though? Like what if
Tiers.
it goes wrong? What do you do? That's why it's like tic-tac-3.
Yeah. Yeah. Exactly. Yeah.
That's how.
Yeah. So you should. Yeah. You have a
For
question?
downward power, could you do a daylight sensor and have like a block cover it from above?
I guess you could. It's an
If it was
interesting idea.
daytime.
Yeah.
But it wouldn't work at night.
I guess it wouldn't. No. You can use torch towers for that, and you can, there's also So we have like a torch. I can show you,
yeah.
And you can also use downward-facing pistons with redstone blocks. That also works. But
The observer tower.
yeah.
Why did the name of that block have a clock in it?
Which one?
The target block.
Oh, I
It
think-
tells you the ticks.
Yeah, it tells you how long it takes to depower. Yeah.
That's
Pretty nice. That's the Redstone Tweaks extra pack. Just download it.
It's not a mod.
No.
It doesn't mod.
So you notice that everything I have here is color coded, and that's just so that my brain doesn't melt.
Yo, it's the YouTuber thing.
Yeah, no.
That's the YouTuber thing.
Like if this was all the same color, it would be impossible to figure out what's going on. Especially like during debugging when you like one block is misplaced and you don't know what's happening. You know.
This is why I tell people in Logic Lab to use different color wires. But they're like, no, always trying to use the same color wires. I'm adding Diego because that's him.
Yeah. And,
You should make everything better with it.
and what else is that like? So you notice that there's a huge amount of wiring just coming out of the logic grid here, or sorry, the memory grid here. And that is not what I was initially doing. That's to make the wiring much easier. Because you can see that I have my 8 wind detectors along this line.
Keep that bitch nice and spacious so you can see what the fuck's going on.
Yeah, you can see what's going on, and it's much less spaghetti, right? So I can show you a previous attempt I had.
think I've seen this one.
I can show you a previous attempt I had of trying to connect everything together. In
I
tic-tac.
didn't realize why Minecraft YouTubers do shit.
Yeah, you had to like squish together, right?
Yeah, so
Yeah.
Oh my god!
So this is a previous attempt. So I had the same logic, I had the same memory grid, right? But I was trying to kind of just jam everything together into the wing detectors, try and get it to work like as small as I could, and just kind of winging it. But it's just terrible. It just doesn't work. Like I didn't even complete all of the like. You have this wing detector here that's not connected to anything. Because I just gave up. It was so, it was just terrible.
Was that what you asked me for help on?
Yeah.
Like, I'm the least qualified person ever, even though it's a game. I feel
Yeah.
absolutely brain
I don't know why I thought about it now, but it looks exactly like an insulin molecule. Yeah.
That is interesting.
It literally just look. No.
I learned that as my years as a biologist. I mean, I was in IB bio, so I learned a lot of biology.
This is why it's really important to like,
As we were learning
kind of draw things out, you know? Like,
Are you really a biologist if you're done learning about biology?
So I can show you guys something.
That's a good logic, bro. You're always learning. When can you call yourself an engineer? You're always learning.
True.
I'm an engine miner.
Very good. Yeah, it's on like 26 t-shirts.
What did Shoot think of all this?
He
thought it was pretty cool.
Did you show him like the
These
full
are
like
pretty
fledged
cool.
out thing?
I mean, they're probably gonna show us this.
You should have invited some professors over.
Yeah, I invited Chu, but he said he had to feed his dogs. Yeah, so I
Oh, cool.
in the schematic I like tried to draw everything out and wire it together before I built it in Minecraft, just so I could like try and figure out how everything should connect together. And that like you don't exactly have to do this per se, but just when you're trying to build something like that, you need to try and plan stuff out because you will have spaghetti and you will tear your hair out and it'll be terrible. Right? Yeah, probably. Yeah. Okay, so let's go back to Tic Tac 3. I don't want to look at that one anymore.
Did you know how to use the schematics feature or application before? Or did you learn it just from Minecraft?
I learned it for this project.
Question.
Yes.
Kid isn't Puck Edition.
I don't think so.
Kick him out.
If you're talking Bedrock, yes.
Bro, what is the redstone abilities of like a nether reactor? You think that had any redstone in
I
it?
don't remember that. It would be an
instant
vertical. Yeah. Okay. Makes a block. Okay, so I can show off how this works. How this works now. Yeah. So does somebody want to play Tic Tac Toe with me?
I already know how to play with
All right, Tim.
I'm about to lose.
All right, so you can go first. Just right-click any button. Just right there. All right.
Oh, you lose, bro? Just be water.
Okay. So I'll go here.
Hard choice, I know.
Very hard. I'm hard.
Damn, that's not optimal.
You're not optimal.
Damn, that's crazy. Everyone that doesn't like that. No, it's not.
Oh, my, this Ethereum.
Okay.
He's throwing. He's good.
You hit the instantly.
Oh my god.
It's fine, Jaskin. Neither of us win.
Oh, you did it, man. Nice. Very good job. Very good job.
We play tic-tac-toe.
Yeah. All right. And so, time detector goes off. So this is time.
Continuously
There you
time.
go. And then we have the reset
See,
button.
I just
over
wanted
here.
to. I just wanted to test this lie detector. Considering that it's only like.
Dude, that transition was clean.
Thanks.
Was.
That was clean.
Yeah. So from the button panel, we have this white line going all the way over here. And what this does, so the way the button panel works is we kind of have the only way to get outputs from a button panel like this is with torches, kind of coming off like this. And so when the user presses a button, the line turns off, right? And so this pink signal is coming from all of the wind detectors and the tie detector in yellow, right? So if either of these turns on, then the game end signal turns on. And when the game end signal turns on, through these blocks here, it will disable the button panel, right? Because it doesn't let any of them turn off anymore if they're all being powered by the game end, right? Wind detection, we built that together, the wind detectors. So we just kind of have 8 of them, and each one is connected to 3 different cells. So this one on the far right here is connected to the top left, middle left, and bottom left. And then this one is going to be connected to the middle row, the column. This one's going to be connected to the right column, and I have them labeled right column. This one's bottom row, and so on. All right, and all of them are just connected together on the green line. The green signal is the wind signal. And then to connect it to the display, I decided to make it orange because I already had an orange line, green line over in the display. And then tie, I kept it yellow. And so if we go over to the display is connected to the memory cells through these purple lines, and it's kind of the exact same method as the wind detectors, but in reverse. Then for wind, tie, and whose turn it is, I just have an extra display module over here connected to whose turn it is, and the game end signal inverted goes into the occupied one. So if the game is over, we don't want to display that it's somebody's turn. We just disable the display. All right. And then for displaying who just won, so if X just won, then that means that they created a 3 in a row, and they placed one down to do that, and so now it's O's turn because the turn flip-flop will flip on every valid turn. So if X just played one and we have an O as whose turn it is, then that means that X just won, right? So we just invert the turn signal and give it to the win memory display module over here, right? So that's it.
These are handy. Man, literally just shows 75% of logic in an hour. Okay. Yeah. Hey, so I have a
Do you
question.
take requests? What's that? Do you take requests?
Sure. What do you want me to do?
I'll do it to his face.
Do you know like maze generation?
No.
Do you know recursive division?
No.
I can tell you after the.
Question for you.
Yeah.
How much have you been messing around with Simulink?
Simulant?
Yeah, like the stuff for junior design.
Oh, here and there.
You haven't looked at it enough?
Not really.
I
I've
want
been
you.
kind of busy.
Yeah, fair enough. Excuse me.
Why not?
Sorry. I'm sure your junior design team understands.
Yeah.
I was gonna say, if you've been looking at Simulink, you should look into it and probably do this there, because if you do that, then you could put it on a PCB.
No, that's actually what I'm working on right now.
Because
Yeah.
if that display looked very simple to the
Yeah.
point where you could get just buy the bits for the pixels,
No, I'm
like
using,
a 8-segment.
no, I'm using
display.
7-segment displays.
Okay,
I
I
always
was gonna
borrow
say
a bunch
8
of
or
chips
7.
and stuff from Eddie. I'm
Yeah.
working on it.
Have you designed a housing for this?
Housing though. It's gonna be.
Ghetto's way to do it.
That'd be
whoa.
Yeah, no, you
Nice
need
one,
something
bud.
new. You didn't get certified in SolidWorks, you can do it in SolidWorks. Hey, well, you can prove yourself. This is the perfect opportunity for you. You have all this time. This is a presentation. Do this in a nice Dude, it's a square with fillet surface.
I didn't say it was.
It's a square, but you got it. I guarantee you can make it in like 2 hours.
I didn't say I can. I mean, I just said, bro, you're doing like.
I want you to do it. Yes or
I heard my
no?
name and I was just like.
I know you the best.
Are there any more questions for me? Any more questions?
Do you want it?
Talk to me after class.
Trying to get that as a professor.
He called it class. Very nice.
Yeah.
Man,
Thank you very much.
How long did this take you? Like a day?
Tic-tac-toe took me a month.
2 hours?
Hey, you really shadowed.
No, I'm saying that.
That thing you worked on all day? You did it in a day, right? This entire thing just one day.
Yeah, no.
No.
This took me a month. This took me 3 different worlds. A lot of pain. Tears.
How much, what
Yeah.
you cut up on your notes?
Don't talk about that.
No.
That's all good.
I have to prioritize, you know?
Yeah, you do.
You can single-handedly.
Nah, you
You
follow
right
you
come first.
you hyperfixate on this. You're following your dopamine.
Alright, so, we're supposed to do, project, Aaron, you can stop by the way.